Oh, hello. Thank you for joining me again. Today we're talking about rates of change in other applications, meaning straight line motion isn't the only time we use the derivative. So today you might be able to start your business degree or perhaps save baby sharks. We're shifting our focus from physics and straight line motion into the world of economics and business. Now, calculating the profits for a company can be quite complicated, so we're just going to focus on what we call marginal analysis as it relates to like fixed costs, revenue, profits. We're going to explore scenarios that are nonlinear in nature. So first, a little bit of vocabulary. A cost function we often write as C of X. That's the total cost of producing X units. The average cost function is the total cost divided by how many units you've produced. And we say it's C, and then that little bar on top shows you that that's average cost. Revenue function is R of X. That's the total revenue for a sale of X units. And then the profit function is pi of X, which is the revenue function minus the cost function. Now, why pi of X? Because that helps them in the business world not to get P, profit, confused with P, price. So they use pi instead of P. So marginal analysis. This gives us a method for estimating how revenue, costs, and profits change when the input increases by one additional item. If not too steep, the slope of the tangent line can be used to give us a close approximation for how quantities are changing in a relatively small neighborhood. Marginal cost, that would be C prime of X, is the rate of change of the cost function. It's the derivative of the cost function. And it approximates the cost to produce one more item. That is the additional cost at the margin. Now, you could find an exact amount, like you could find the cost of X plus 1 and subtract the cost of X, but maybe you don't have that available to you, or approximating is quicker. Let's just see what happens. Example 1. The cost to translate documents into another language is a function of the number of pages. And the cost function is given by C of P, 0.002 P cubed minus 0.1 P squared plus 8.75 P. So calculate and explain the marginal cost at the production level of 10 pages, and how does this compare to the exact cost to translate 10 pages? First of all, we take the derivative of our cost function. That's the marginal cost, or the additional cost at the margin. So for our cost function, its derivative will be 0.006 P squared minus 0.2 P plus 0.875. We're curious about what that looks like in the 10-page range. So I got $7.35 approximately. And that means if you've produced 10 pages, the cost to produce one more is $7.35. Let's compare that to the actual cost to produce one more. The cost of 11 minus the cost of 10, which is about $7.31. So really, really close. This is a graphical representation for average cost and marginal cost, okay? So we're working between the 100th something produced and the 101st something produced, okay? So at 100, the Y value is the cost of producing 100 widgets or whatever. If you produce 101 widgets or whatever, then the cost goes up. So this purple box here is the cost of producing one more widget. So if we want to approximate, we can use the tangent line. And instead of figuring out the cost of that 101st widget on the cost function itself, let's find it on the tangent line. So now this green box is the approximated cost of producing just one more. The cost of producing a set of Bluetooth headphones is given by the production manager as C of x equals 1500 plus 50x plus 0.01x squared. Where he came up with that equation, I have no idea, but we have it, we're going to use it. Part A says to find the marginal cost function and then use this function to estimate how fast the cost is going up if the company produces 100 sets of headphones. Step 1, find the marginal cost function, that's derivative of the cost function. Then we can plug in 100. So the marginal cost is $52 per headphone. I graphed it there for you. And you can see that that marginal cost doesn't stay true forever, does it? After a while, it's inaccurate. Part B says, compare your result from Part A to the exact cost of producing the 101st set of Bluetooth headphones. So we'll take the cost of the 101st, subtract the cost of the 100th, and we get 52.01 for the 101st headphone. Pretty close. Find the average cost function and evaluate the average cost of 100. So again, the average cost function is total cost at a certain amount of widgets or headphones divided by that amount of headphones. Total cost divided by the number of headphones. Plug in 100 to that, and the average cost for 100 headphones is $66 per headphone set. In other words, when 100 headphones are produced, the average cost is about $66 per set. Now, suppose these new Bluetooth headphones, from example 3, sold for $125. Write the revenue function. Well, the revenue function is just 125 times how many you've sold. From there, we can write the profit function. That's the revenue function minus the cost function. We clean it up a little bit. You get negative 1500 plus 75x minus 0.01x squared. Compute the marginal profit function if 100 sets of headphones are produced and sold, and then interpret that. So if we take the derivative of my profit function, we get 75 minus 0.02x. If you plug in 100, that gives you about $73. What does that mean? When 100 headphone sets are produced and sold for $125, the profit is increasing at a rate of $73 per set. Now, see, this is the million-dollar question. How many headphones should the company produce in order to maximize their profits? Profit is maximized where the marginal profit function, the derivative of the profit function, is 0. So we'll set it equal to 0. And if you solve for x, we get 3,750. So the company should produce 3,750 sets of headphones if they want to maximize their profits. If you look at the graph, I've graphed revenue, cost, and profit. And see the maximum of profit is about right there. And you can see that's the biggest gap between cost and revenue. This is another graphic representation of this. In the graph shown at the right, the break-even points occur where the revenue equals the cost. A company would obviously be most interested in knowing how to maximize profits. The maximum, or minimum if it's not going well, can occur where MC equals MR. In other words, the cost margin equals the revenue margin, or the slope of the cost equals the slope of the revenue. Right here. And again, you can see that's where the difference between the cost and the revenue is the biggest gap. However, maximum or minimum profits can also occur at endpoints, so beware. Now let's look again at the graph of our example, and you see the equation of the tangent line here is where profits are maximized. Okay, away from business now, let's talk about sharks. Gabby is working on a project that watches the decline in great white sharks in the Atlantic Ocean. The function S of t equals 3750e to the negative 0.2t gives the number of sharks t years since she began working on the project. Find the rate of change for the number of sharks in the ocean after 3 years. Okay, so rate of change, that's a derivative. So we need to find the derivative of our population function here, and then plug in 3. So negative 391.8515. That means that shark populations are declining at a rate of about 392 sharks per year after 3 years. How about sugar gliders? Omar uploaded a funny video of sugar gliders on his Instagram account, and the video went viral rapidly. The number of views, t days after Omar uploaded the video, can be modeled by the function v of t equals 243e to the 0.5t. Omar is a genius because he came up with that. What is the instantaneous rate of change of the number of views 5 days after he uploaded the video? Right? If we're doing instantaneous rate of change, you need the derivative. And if we want to know the derivative at 5, you plug in 5. 1,480, what does that actually mean? Remember, this is a rate. After 5 days, Omar's video views are increasing at a rate of 1,480 views per day. That's pretty good. Example 6. Use the following table of values for the number V of t of gallons of water in thousands per hour H that are flowing into a retention pond t hours after a severe thunderstorm. What? So V of t is gallons of water per hour. So just note, V of t here is already a rate. So what is the interpretation of V prime of t? V prime of t is the instantaneous rate of change of the rate of flow after t hours flowing into the retention pond. So it's a rate of a rate. Part B asks us to estimate V prime of 2. We have a value for V of 2, but how would we find the slope there? Well, you can look at the 2 points on either side and use a regular slope formula. So 1.24 minus 0.93 over 2.5 minus 1.5, 0.31. So that would say that after 2 hours, the rate of flow of water is increasing by about 310 gallons per hour, because remember, this water is in thousands. When does the rainwater begin to slow down? And estimate the instantaneous rate of change at this time. So look at the table. What's going on there? When does it start to slow down? Well, it's going increasing, 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 increasing. Aha. Now it looks like it's decreasing. V of 2.5 is greater than V of 3. So somewhere between 2.5 and 3 hours, the rainwater flow begins to slow down. If we want to estimate that, we'll just find the slope there. So V prime of 3 is approximately equal to maybe 105 minus 124 over 3 minus 2.5, negative 0.38. So between 2.5 and 3 hours, the instantaneous rate of change of the velocity is about negative 380 gallons per hour squared, because remember, this is a rate of a rate. So again, derivative is not just straight line motion. Derivative just applies to all kinds of stuff out there in the real world. Thanks for joining me at the beginning of your business degree, and thank you for saving baby sharks. See you next time.